initially, and then we can solve all the problems listed under the section. Initially, and then we can solve all the problems listed under the section. The first concept that I'll be teaching you is the digit concept. The first concept that I'll be teaching you is the digit concept. Remember one thing. This is a very, very important concept. Is the digit concept. Remember one thing. This is a very, very important concept. Because if you know how to play around digits, then you'll be able to solve most of the problems in basic maths. So let's understand the digit concept. Imagine I give you a number like 7789, the number that I'm giving you. Now I ask you to perform extraction of digits. I ask you to perform extraction of digits. So let's learn the extraction of digits, and after that you will see how we can implement the extraction of digits most of the problems. Okay, so when I say extraction of digits, what does it mean? It means I need 9, I need 8, I need 7, I need 7, I need all the digits individual. Okay, so what is this digit 9? Can I say this? If I do a modulo 10, I'll actually get 9. Now you might ask why. If I ask you the numbers that are divisible by 10, what are they? 10, 20, 30, 40, 50, 60, 70, so on, 100 and so on. Do you see a pattern? All the numbers that are divisible by 10 are actually ending with 0. Is it? Right? So can I say, if I'm doing a modulo 10, what is the meaning of modulo operator in basic maths? The modulo operator says, I will divide the number by 10 and whatever is the remainder, that is what I'll give you. So if I say, if I'm dividing this number by 10, what is the nearest number? Obviously that will be 7, 7, 8, 0. If I divide it by 10, this is what the nearest number will be. And can I say that the remainder then will be 9? Because if I divide it by 10, then this is where the division, like this is the number which will get divided by 10. And after that, we'll be left out with 9. That is why when you do a modulo 10, you always get the last digit. So you get the last digit as 9. So this is how you get the 9 digit. If I ask you, can I get the next digit 8? How will you get the next digit 8? Very simple. You say, okay, this number, let's divide it by 10. So if I divide 7789 by 10, can I say I'll get 778.9? Can I say this? If I divide the number 7789 by 10, I'll get 778.9. And if I take an integer round off, if I take an integer, in order to go to the next step, you will say divide by 10. If you do a division by 10, you'll actually get 778.9, but you just take the integer part. That is why you get 778. So once you have 778 with you, if I need the last digit, which is 8, how do you extract it? Again, the same way, you say, can I divide modularize with 10? If I do a mod of 10, I'll actually get 8. Why? Because the nearest number will be 770, which is divisible by 10. which will still leave a remainder of 8. So I get the digit 877. Why? Because if I write 778 by 10, I'll get, again, if 7 number that is divisible by 10 to 7 is 0. Thereby, you get a remainder of 7. So you get 7. After that, if you again try to divide it by 10, this time you'll end up getting 0. Because if I take 7 divided by 10, it'll be 0.7, and extracted all the data. That's how you look like. Can I say, if I have the n, I can take it from the user. I can take the n from the user. And imagine I'm asking you to print all the digits, extract all the digits like 9, 8, 7, 7, and you can print it. So how will you do it? It's very simple. I will be like, okay, while I know what is the last step. Last step is the extraction goes on from n when it is 7789 to n till 0. So I'll be like, I'll go on till n is great. Extraction is very simple. The first time n was 7789. So if I had to do an extraction, it's very simple. Can I say the last digit is nothing but n modularized 10? If I do an n modularized 10, I'll get the last digit 9. And in order to get the next digit, what I do is I say n is n by 10. And this is how I can do it. So what will happen? Let's do a dry run. At first, imagine the user gives n as 7789. So this says 7789 greater than 0, which is true. So the last digit happens to be 7789 modularized 10. Hence the last digit is 9. If you want to print this last digit, you can definitely put a print operation. In C++, it is cout. In Java, it is. So I say if you do, what will be the value of n now? Can I say the value of n will be 9? It goes 7 greater than 0. Last digit. And this time it will be 7 of the in the reverse concept. So now let's look at the first problem. It states count digits. Let's understand the problem. Given the number n, find out and return the digits present in a number. Very simple. It says 156 is the number, and the number of digits digits is 3. Imagine the n is given as 7. It has just 1 to my as fraction or fraction. We give try to count that it is running absolutely fine. And then I'll go ahead and submit this. So this is how you can easily solve this particular. Now remember one thing, this last digit does not have any significance. So you can remove it. So that was for extraction of digits, but this is kind of reducing the numbers. So the number of times it is divisible by 10 is the number of times the digits are. Logarithmic. The calculator will actually get something like 3.89 something. So this is the value that you'll get if you do a log base 10 of the number. And then if you can add a 1 to it, this will be 4.89. And if you take an integer of it, that will be 4. So this is another way to find count of digits. What you do is very simple. You say count is equal to log 10, the number plus 1. And you're saying take the integer, or you can just auto cast it, like typecast it to integer. This is how whatever you get, this is converted to an integer. If you're getting 4.89, it'll be truncated to 4. And scope log 10 was not declared. So if you find such errors, what you can do is might will start working fine. So once you've done this, you can go and compile and you're seeing that as well. But the primary concept is extraction of digits. Log base 10. Why log base 10n? The reason was very simple. You saw this is getting divisible by 10. How many times is the loop running? The number of times it is getting divisible by 10. So this is why you will say time complexity is near about log base 10n. This problem count digits. The next problem is reverse a number. Let's go to the problem. It states write a program to generate the reverse of a given number. Print the corresponding reverse number. If a number has trailing zeros, then its reverse will not include them. For an example, the reverse of 10400 will be 401 instead of 00401. And these are some of the examples. So let's get back to our extraction of digits concept. So according to the problem, what they are wanting is, if I'm giving you the number 7789, the reverse of this number will be 9877. Now we know that the extraction of digits happens in the reverse fashion, where we generate 9, then we generate 8, then we get 7, then we get 7. Somehow we need 9877, which is the similar fashion. This is where the basic maths comes in. What you do is, you define a variable, sum, or maybe reverse number equal to 0. And you say reverse number equal to reverse number into 10 plus last digit. Remember this. This is what you say. Reverse number into 10 plus last digit. Let's see how it works. So I'm saying initially reverse number is 0 to start off. Let's do the step by step. First step, 9 gets generated. So what am I doing is 0 into 10, because reverse number is 0 at the first step. At the first step, 7789 modulo 10 will generate 9, and n would have as of now become something like 7789 by 10. So n would have as of now become 778. And reverse number says reverse number is 0 into 10 plus the last as of now then 0, and 778 modulo 10, hence the last so the 10 plus 7 is 9877. So you got the reverse number at the end. Why it's simple? Why did this work? It's very easy. Or rather, the reverse number as of now is 9, right? This is what the first iteration is. Let's do the next iteration. So the next iteration will be like, I'll just quickly omit this off. Number, this is last digit. You're easily getting the last digit 9. And after that, you're getting the next last digit 8. And you somehow want to add 8 to that 9. You somehow want to add 8 to that 9. And the easiest way is, if you can somehow add a 0 to this 9, it will become 90. And then if you add a 8 to it, it will become 98. Similarly, if you want to add 7 to it, if you want to add a 7 to it, make it 987. You again add a 0, and then a 7 to it, it becomes 987. Again, if you want to add a 7, you again add a 0. This is why at every step I am doing reverse number into 10. Whatever you have generated into 10, that will allow the last unit digit to be 0. Then when you add a digit, goes and gets into that place. As simple as that. So again, you saw that extraction of digits is actually handy. So what I'll do is I'll take the number and I'll keep the reverse num equal to 0. And then I'll go ahead and say n greater than 0. And I can say last digit is n modulo 10. I can say reverse number is reverse number into 10 plus last digit. And I can say n is n by 10. And at the same time, I can say C out of reverse number is what I need. Perfect. And I'll quickly this So next problem is check palindrome. Now when I go to the palindrome problem, let's understand the problem. It states write a program to determine if a given number is palindrome or not. Print true if it is palindrome, or false otherwise. So over here it states palindrome are the numbers for which reverse is exactly same as the original one. For an example, 1 to 1. Because if you take 1 to 1 and you do a reverse of it, 1 to 1's reverse is 1 to 1. That is why it is called as palindrome. So if I go to the iPad and I write some other palindrome numbers, it's like 1331. If you write the reverse of it, it stays still 1331. Something like 11. 11, any definition of palindrome number says reverse of a number. So if I somehow can generate the reverse of a number, if I somehow can generate the reverse of a number, which I've already did, and then compare it with the original n, and if they come out to be same, can I say they are palindrome? I can. So over here, if you remember, we took a reverse number, and at the end of the day, the reverse number was nothing but the reverse number. And now, if I can compare this reverse number with the original number, which is n, and if they come out to be same, I can say it is palindrome. Like if this is true, I can say it is palindrome, or I can say it is not palindrome. Can I say that? But wait. If you remember, we were dividing n by 10. And at the end of the day, n was 0. So does n have the original number? No, because we are doing operations with n, which has made n to be 0 at the end of the day. So what I need to do is, maybe I need to store a duplicate of n in some dup variable. And instead of comparing it with n, I can compare it with the duplicate, because n will be 0 at the end of the extraction of digits. It's very important to store a copy of n somewhere so that it can be used to compare it with the reverse of a number. That is the only change that you have to do. And that is the only thing that you have to keep in the mind. So if you remember, this was the code. So what I'll do is I'll just go ahead and say duplicate equal to n. And over here I say if dup is equal to reverse number, I can go ahead and print true, which is what they want, which is true, or else you can just go ahead and print false. That is what they required. Okay, with a small. Now quickly run it and see if it is running fine. Should be, and let's quickly submit this. GCD or HCF. But before that, we will be solving Armstrong numbers. So, what is the definition of Armstrong number? It's very simple. Imagine you're given this number 371. You take 3 cube, 7 cube plus 1 cube. If taking the cubes of these numbers, like cubes of these digits, and adding them up, sums up to the number itself, that is what you call as an Armstrong number. Even if you take 1634, 1 cube plus 6 cube plus 3 cube plus 4 cube, if you sum them up, you actually get 1634. But something like 35, if you take 3 cube plus 5 cube, this is not going to be equal to 35. This is going to be equal to 134. So this and this are not same. Whereas 1634 and the summation of cubes of its digits is 1634. So you call 1634 as an Armstrong number or 371 as an Armstrong number. So I hope you've got the definition of Armstrong number. So if you have got the definition of Armstrong number, you know how to solve it. I've already taught Armstrong number. So if you have definition of digits, you know how to solve it. The definition of extract 8. You know how do you extract 7? Can I say sum equal to sum plus last digit multiplied thrice? Last digit into last digit into last digit. Can I do this? So first time 9 comes in, what happens? 9 into 9 into 9 gets added to sum. Next time 8 comes in, 8 into 8 into 8 gets added to the sum. So everything is getting added. First time 9 into 9, 9 into 9 into 9 got here. Next time 8, again 7 came in, 7 into 7 into 7. So can I say at the end of the and this not, it's not an Armstrong. Again, what logic works? You have to compare if this and the duplicate are same. If this is, then you say it is an Armstrong. If this is not, it's not an Armstrong. Again, what logic worked? is print all divisors. So when I say print all divisors, what does it mean? Imagine I take a number like 36 and ask you, what are all the numbers that divide 36? So you can say 1 is something which completely divides 36. You can say 2 is something which completely divides 36. You can again say 3 is something which completely divides 36. 4 is something which completely divides. Is 5 something which completely divides 36? No. If 36 is divided 5, it leaves a remainder of 1, so not 5. 6 is something which does it. 9 is something which again does it. Then 12 is something which does it. Then 18 is something which does it. And then 36 is something which does it. So if I talk about 36, the divisors of 36 are 1, 2, 3, 4, 6, 9, 12, 18, and 36. These are the divisors of 36. The question is very straightforward. You have to print all of them in this particular order. Okay. Now, how do I do it? It's very simple. One thing I know for sure is if I'm talking about divisors or factors, then anything greater than n will never divide n for sure. So if I know all the divisors are going to be between 1 and n, can I just loop from 1 to n? That's my first thought process. Since I know the divisors are from 1 to n, my first thought process is very simple. So let's do one. Let's start the loop from I equal to 1, I lesser than equal to n, and I plus plus. This is something I know for sure. So I is used to loop around. Now the first value of I is 1, then it's 2, then it's 3, then it's 4, then it's 5, and then so on till 36 in this case, if it is n. So how do you determine that this I, if it is completely dividing, if I is completely dividing n, then it is a factor or a divisor. And what do you mean by completely dividing? It should leave a remainder of 0. When I say leaving a remainder of 0, does it mean if I do a modulated of I, if I do n modulo I, the value should be 0 because it's completely divisible. By what I will do is I'll say, okay, if n modulo I is equal to 0, I will go ahead and print I in C++ cout in Java system.out.println. I'll go ahead and print out I. So in this way, I'll be able to print all the factors of a particular n. If I talk about the time complexity, ask you what is the time complexity of this code, you'll be like, Trevor, it's very simple. Since the loop is running from 1 to n, it's taking n iterations. And this is an unit operation, so let's not calculate it. Thereby, the time complexity of this particular approach is nothing but big O of n. Very simple. Over here, they've given us everything. They want us to write this print divisors function. Let's write the print divisors function. It takes an n, uses cout, I, and then you. And on submitting, you will see that this much better way. I can. As a factor, one has to be multiplied with something in order to get 36. So one was multiplied by a small number. If I go back to the code, what did I say? Root of complexity. Something before discussing the time complexity, you're writing I lesser than equal to square root of n. Got it? I can say I've also done print all divisors in both the ways. Now, what is the next question? It states check for prime. So, what is the definition of a prime number? A lot of you will say a number that is divisible by 1 and itself. This is a wrong definition. Why? Because according to this definition, 1 is a prime number. Because 1 is divisible by 1 and 1 is divisible by itself, which is 1. It's a wrong definition. Instead of this, the definition that you should always keep in mind is a number that has exactly two factors, 1 and itself. That's a better definition. 1 and itself. A number that has two factors, which is 1 and itself. So, if you remember, we just now computed factors. Right? So, if you're given a number, something like 11, can I say 11 has a factor of 1 and 11 itself? Any other number doesn't divide 11. So 11 is a prime number. If I say 13, 13 is a prime number because 1 and 13 divides it. If I say 5, 5 is a prime number because 1 and 5 divides it. If I say 4, 4 is not a prime number. Why? Because it is divisible by 1, it is divisible by 2, it is also divisible by 4. So there are three factors. So 4 is 2, 4, 8 divisible will exactly has two factors. So way to check is I will do one thing. I'll keep a counter equal to 0 and I know it exactly has two factors. So I'll run a loop from 1 and I'll go until n and I'll say I plus plus and I'll say, hey, listen, if it is a factor, it will be completely divisible by I, hence it will leave a remainder 0 and I'll do if the counter turns out to be 2, then I'll say it's a prime number or else it's not a prime number. So can I say this is the extreme brute force approach? And if I write the extreme brute force approach, what n 30 other you that is definitely a factor. The other factor is different, then it will also be counted. And then you can have a same check. If counter is equal to 2, prime, else not a prime number. As simple as that. And if I talk about the time complexity, this loop ends up running for BGO of square root of n. So if someone is coming up and asking you, how do you check for a prime number? You say, I know the square root method because I know the observation. For every factor, there is the other corresponding number with which it has to get multiplied in order to get the number. Thereby, I'll go to 9, greatest common and 12. So if I write down all the factors of 9, it is 1, all